Doesn't matter?
It's okay.
Okay, fine.
好，那我们就开始第二个 session。那第二个 session 比较特别，我们这是第一次尝试用全程英文的部分来跟各位做分享。那今天非常开心的是由政大地政系我们的 Stephan 我们的这个副教授呢来帮我们介绍这个有关于遥测应用在一些突发灾害分析这个部分。那 OK，
Okay. Well, yes. Thank you for your invitation. Thank you for having me. I wanted to talk a bit about not the overall concept of remote sensing or hazard assessment, but also a bit about my background and what we could theoretically provide. So there's some personal background I'm going to talk about and two topics that I'm going to address here. That's one is spatial temporal information systems and remote sensing, a combination of both. And the other thing is remote sensing data analysis, which builds on top of the other one. So, and of course, there will be also some slides about developments, development fields, and future prospects. So, my personal background, actually, I was trained as geologist in engineering geology and hydrogeology with fields into geomechanics and geophysics in Germany, in an old mining university. My research background, beginning in the 2000s, is focused on remote sensing and in particular on planetary remote sensing. Okay, so come back to that later. Lots of data and lots of diversity. So project background, lots of projects that we have run, mostly in space mission exploration. And my development fields or my publication fields are actually fundamental research, but also applied research in mainly geographical information system and technology. So if I put chapters on my past activities, I would say, okay, it began with some 3D and 4D GIS developments in engineering, developments of temporal aspects for common geographical information systems, combination of temporal aspects with database management systems, which is going to be important. Hazard assessments for planetary surface studies, I come back to this, and decision support systems. And, well, small scale, large area mapping, which is going to be a challenge and which also applies to, let's say, hazard analysis and hazard monitoring. So one could say, okay, one has to do with space models, real 3D space, not 2D. Time models, one has to do with managing data volume, and the other one with managing big data, large data extents. And these are the main topics, actually, that I also address here. So motivation, actually, for all my research, and which goes into the topic that we are talking about in hazard assessments, is that we really need to find a way to employ temporal data models. Because if we talk about processes, they are always coupled with time. And modern GIS, modern geographic information systems cannot handle time. So this is really something that needs to be worked on. If you want to understand processes, you need to understand time, and you need to implement time. Volume models is also important, of course, not just for mining applications, for example, or other aspects, but we need these volume models if we talk about, for example, landslides. We just don't talk about the surface model itself, but also about the volume model and the different, the heterogeneities that such a landslide can have. Large volume data is another issue. So storage is cheap. That's not the problem, but the problem is that we need to access that data to really get as much data into our modeling and as much data into our interpretation as possible. And the same is with large data extents. So it's not just looking at a single spot, but we need to look at the bigger picture. And bigger picture means more data and more temporal data, data of the past, data of the present. So these are the challenges, basically. So one thing I started with as a student already was for GIS developments, 3D and 4D GIS developments. The project has finished already many years ago, but that was a project designed on developing a 3D and 4-dimensional GIS system for tunnel exploration and dam engineering. There have been lots of spin-offs. It was all built on an object-oriented database. It's built on a CAD system that was really like refurbished, you know, and not the CD system, but the user interface. And it has been extended to even virtual reality aspects that you can walk through tunnels and engineer constructs. So it was applied for the Gotthard-based tunnel, some applications there for structural modeling in hydro dams, and also most recent project was for subsidence modeling caused by mining. Okay, so that was one of the projects that the Gotthard-based tunnel, where we also have lots of close to horizontal drillings to explore the geology, and these were also visualized using the system. So, but my main dish actually, beginning in the 2000s, was focused on mapping and on planetary mapping, geologic mapping, large area mapping of planetary surfaces. So we have a totally different database available there, and it goes far into the petabyte data range already, so that we have to work with if we talk about global work. So one of those things, if you talk about geology, you always talk about 3D, and you always have to talk about time, because time is crucial part of geology, and this is how geology is defined. So how do you deal with this? In modern geographic information systems, you just usually map, and that's it. Maybe you do some measurements, but how can we really address, like, query temporal data? That was one of the questions that we had. So not just mapping extents and mapping lithologies, but also querying what came first, what came after, and more complicated constructs. So that was one thing that was published a couple of years ago on combining the stratigraphy with the chronology and merging time and space in geology into some query language, designing a temporal data model, and providing I would call it an access model, how to query these kind of data. That was later implemented as a user interface also. I don't go into the details here, just showing you that there has been some work was invested in conceptualizing this temporal and spatial idea, and to apply it actually. So, but of course there are other topics on planetary surfaces that find more direct application in Earth cases, for example. So for the ESA Lunar Lander, the European Space Agency, they considered, and they now reconsider sending a lander to the moon, to the South Pole. And with that, a couple of questions arise. One thing is there enough light on the South Pole of the moon? Because the light is coming in very shallow angle. So, which means if we talk about light and variations, we again talk about time. So this is it's not just seasonal variations, but daily variations, hourly variations. So, lighting conditions means temporal studies. On the other hand, we also need to have high precision terrain models to actually know where the lander is going to be and where the light is coming from, and how it hits the target. So that was another thing. And of course, the geostatistical, the spatial analysis that has to be made to model all these features. So this work has been published here in PSS, Data and Space Science, quite a big paper. Our contribution was related to the terrain modeling, definitely, to the analysis, and to one thing that is quite common on planetary surfaces, on actually modeling the impact craters. And impact craters, this is also a topic that we dealt with from insurance companies on Earth, because they wanted to know if meteorite impact is going to pose a hazard for humans, and then how that should be addressed in their insurance policies. So here in this case, we are talking about the moon. These hazard assessments were just simply because we need to make sure that the lander was just safe and not just, you know, on an inclined surface and not operating potentially. So that was the reason why these features have been mapped, and commonly in planetary sciences, these features are mapped by hand, which means if you're a good counter, you arrange like 500 impact craters per hour. Here we are talking about a couple of thousands, larger areas, high resolution, easily have 20, 30,000 impact craters. So you can calculate how much time you will need. And well, you can't, that's the problem, you can't employ a monkey to do this, because you really need to know how an impact crater really looks like to determine the diameters and everything. So what we get are standard frequency distributions to derive the statistics, but it has to be precise, of course. And in this case, it was needed for the lander. Another approach that was published 10 years ago by a colleague from Korea, where we worked with, is actually using automatic procedures to auto-detect these features, like impact craters, or maybe like big rocks, which is also a hazard. So lots of work has been invested there, and there are procedures to actually automatically detect impact craters, boulders on the surface to derive statistics. And the results are quite promising, but still manual interaction, manual mapping is still more precise for different reasons. Mainly because of degradation states. What you can see here, the situation is not just like an impact crater, but it's more complex. Shapes are overlapping. Okay, so and because of lots of limitations in commercial GIS systems, such analysis tools were implemented in Esri's ArcGIS, for example. Also something like what's not implemented yet is geologic measurement tools, so that we can work with terrain model data and ortho imagery to outline areas to measure not just slopes but also layer altitude, and to do what is usually done in other software packages that you have to buy outside of any information system. But we just wanted to have a solution which is just not jumping from one software package to the next, but having one solution in one package. This is why we used Esri's platform to also implement functions for geological analysis, as you know. Also. Okay. Okay, so these analysis tools, these hazard assessment tools, converge later into a more like to come to a decision support system, to gather information, to merge this information, and to say, okay, my requirements are like this, this, and this. These are my input variables, and let the system run, gather all the data, which was certainly a management problem with this amount of data, analyze this on a global scale, here, for example, to arrive at, for example, safe landing spots. Okay, so it's not just terrain models; it's also image data. It's high precision terrain model data that has to be reprocessed iteratively. That is also temperature data and thermal data, or remote sensing, of course. So that we finally could spot certain locations which are safe to land. Yeah, well, and this outlines this in a bit sketch way. So there are requirements from the science side which say, okay, we just can go there, we just have to land there or there. There are some places, but there are also low-level constraints posed by engineering. So they say, okay, it's nice that you want to land there, but it's simply not possible because the slopes are complicated, or too many boulders, or too many craters, or whatever. So, or the atmosphere pressure is not high enough. So this was another thing. Other engineering constraints on a higher level, there were lots of interdependencies, and all this went into this decision support system that we started to develop to come at least some rating systems of areas that are good and that are not that good. And this sort of assessment things can easily be transported to Earth cases. So terrain model data is available, it can be processed. There's lots of image data that can be used, that can be processed. There's lots of auxiliary data, non-spatial data, whatever you need, you just merge it, and you can work on finding algorithms to really like analyze this data automatically. Would be the best case, but at least to prepare it for experts to look at it. So that was the development on the GIS side. But there's also, of course, remote sensing, spatial and data analysis, which is also implemented in GIS, but which focuses more on the analysis. And the main focus here is on small scale, large area mapping, which is the problem because of the data amount that is there. So one of the big projects that we had was well, not a big project, but that was a research project with colleagues across Europe. It was called Mapping the Northern Plains of Mars. So planetary research is not that exotic anymore. So there are lots of mutual benefits, I would call it. Because in the beginning, there were just planetary scientists, there were Earth scientists, and in around 2000 or so, when new data came available, when hyperspectral data became available, there were lots of actually terrestrial Earth scientists that were interested in applying their knowledge to planetary processes. And in the same way, we have been dealing with lots of data and lots of remote sensing studies. So there's also a return of what we do in the case of Earth sciences. And this is one of those projects that had lots and lots of data available. And we just wanted to create a geospatial model of how the northern plains of this planet developed. So we picked some traverses, 3 traverses, and analyzed landforms along these traverses to find spatial signals and a correlation between these features. So the project is not over yet. We are still working on this. So one part was definitely on the left-hand side, the landform mapping, just to identify landforms. But the resolution, the image resolution goes down to even below 1 meter per pixel. So you can't do this, and it's impossible to do this on high resolution. So what we needed to do is find a system to subdivide this whole area and create a mapping, which is called grid mapping here, that goes into is the landform present or is it not present? So if it's present, just say yes, okay? And so we come up with 15 landform maps, and we can now start to correlate these landforms with each other. Are there correlations between different landforms? But we also could correlate this with like water abundance, atmosphere, temperature distribution, soils, and whatever. Okay, so that was the idea, and to come up with a meaningful expression, a meaningful correlation. Okay, so as I said, this work is still ongoing. So currently we are still debating which methods are actually best to employ for these cases. Self-organizing maps came up recently, so we are looking into this to find correlation patterns, and this will, well, sooner or later end up in a couple of publications because there were teams on each of the 3 sites. Back in my time in Germany, we were also working on processing of, well, large volume remote sensing data, because we had a participation in one remote sensing experiment, which was still systematically observing the planet Mars at high resolution and stereo. So the high resolution stereo camera is one experiment operating since 2004. It's creating image data up to 10 meters per pixel. Still everyday imaging, so you can imagine what kind of data volume is available right now. And the art now is to merge all this data into global mosaics for the science and for the public to use further. So the result is, because it's a push-broom scanner, okay, it's not just a frame, it's a push-broom scanner. We have these strips across the surface, and because it's just integrating, you also have illumination variations. It gets darker or brighter or whatever. So the idea is actually to merge all these data sets in 4 channels: red, green, blue, infrared, and the panchromatic, and to create these mosaics at high resolution. So that is one part which is also still ongoing and will be ongoing for many years. And the other thing is how to distribute that kind of data for the general public, okay, because they are paying for that. They want to know what's happening. So, and this is where we've been working the last 3 years on a platform which was called iMars. You can also visit it and play around. This is a web GIS system with layers you can click off and click on. So that's not the art, but the art is actually to have a temporal slider, which is quite innovative. That's, I would say, one of the first ones. You know this maybe from Google, because they also have a temporal slider, but this is a different implementation. So we can look, you can search for data and really search for data and see what changed in terms of coverage. So it's quite nice actually to look into this. Okay, other things now at NCCU, there are processing pipelines already partly established. So there are ideas how to process, for example, SAR data, volume SAR data, or to use that data to establish, like, because there's 12-day repeat imagery, to use that data, to process that data, and to analyze surface deformation. So this is one case Dr. Lin has been working on. You might see these green dots here. You can see them more clearly here. So these are all places where subsidence on centimeter scale has been detected, so where some vertical movement takes place on very small or very large scales, okay? Tiny amounts of vertical movement. And this is really interesting to establish something like that with the data that is already available to systematically monitor areas, for example, also here in Taiwan. Okay, so to conclude everything, I come up now with 4 slides with some ideas how this background could merge into something for future applications. So, so there are 4 challenges, I would say. One of them is the mapping, systematic mapping of spatial and temporal extents, creating spatial-temporal data models for data integration. So the data models is the crucial thing here. So we have lots of data of different kinds, different varieties. How can we merge them into one spatial-temporal data model that can be accessed, and that can be used for mapping, that can be validated, in particular with field data that is available, and that's so important. And to get a system which allows us to spot these features and to automatically extract them. And if I say sample feature extraction and learning, we are going into the area of machine learning. Okay, so these are construction sites. This has to be really done. Data is output, maps are output, but also feature models that can be used for further applications. The second challenge is the monitoring. How can we implement something that can really, like, on a 10 days, 12 days, 15 days, 1 month basis to repeat and image and use the image and radar data and terrain model data to spot difficult locations, problematic locations, hazard locations. So that's what I call the monitoring model, and this is closely coupled, as you see, with the feature model that we have here, the mapping model, the monitoring model, and of course, once we have all this data, we need to do something with this. And it's not just observing that there is something, that we spot a landslide, that we spot a debris flow, that we spot any other feature, but we want to make sure that we put all the variables into one system to see if there's a signal. Okay, I mean, we know this, landslides are triggered mainly by rainfall, but not exclusively. There are other factors that influence landslides. You know this better than me. So how can we correlate all these events? The surface topography is one thing. The weather is another thing. Earthquakes are different things, and human construction and whatever comes. So that's the idea, to create statistical models, but we can't do this on a global scale, of course. These are just, we just have to look into some of these interdependencies. But the data is available, so we just need to employ this data to come up with some, maybe one day even with a prediction model. But there's lots of work to do in this case. So, and of course, and this is why we're doing all this, is, well, to find ways to mitigate the risks, okay, to also not just to spot these problems, but also to find ways to lower the impact, actually, sooner or later. So we know that these features impact infrastructure, they impact lives, they impact people and their housings and whatever. I was a bit inspired by a work that was done many years, not so many years back, like 6 or 7 years back, where you see this map here. This is OpenStreetMap. And this shows the downtown of some downtown area in Port-au-Prince, I think it's Haiti, where a study has been done on how did this whole picture, this map, and this is a map on OpenStreetMap that you can click, which helps people if they're in danger, if there's a problem, they know where to go, you know. And this map has been expanded like exponentially after or during the earthquake of 2010. in Haiti. So in the beginning there was nothing, and as soon as the earthquake came, people were just obsessed in adding places where they can find water, where there's shelter, where they can hide and whatever. And this analysis has been done with the statistical data that was available. And the same thing was also done with Fukushima, with the Fukushima event. So before there was essentially nothing in terms of where can people go, where and how to mitigate. And during the event, people started mapping to show other people where they can hide and where they can go. And I think there are there's some overlap topic-wise if we think about locations here that are close to slopes, to mountain areas, okay, that suffer from the impact of typhoons, for example. So to build such models, and that's the basic motivation, actually. Okay, and yes, and with that, I would like to conclude and say thank you for your attention.